talked about experimental and theoretical probability. We compared the two. Experimental probability is when you do an experiment or a trial, what does happen. Theoretical probability is what should happen. Today, we're going to talk about how to find the probability of two or more things, and it's called compound events, two or more things. One of the things we talked about yesterday is in order to figure out the probability of something, we need to know what all the possible outcomes are. And so sometimes we have to actually do some math to figure that out. For example, yesterday we had a question about what's the probability of rolling a 5 or two dice that add up to a 5. And we had to figure that, we couldn't figure that out until we figured out what all the possible outcomes are. That's what we're going to study with this first foldable. And so in order to figure out all the possible outcomes, we call that a sample space. You can write this anywhere. You can write it on this foldable. You can write it, say, in your notes. But a sample space is a list of all the possible outcomes, because this is going to give us our bottom number when we're trying to figure out the probability of compound events. We have to figure out what the sample space is. What are all of our possible outcomes? There are a couple different ways we can do that. We can use a table, we can use a tree diagram, or we can make a list. And just to kind of give you a sneak peek, I'm actually going to use a tree diagram to make a list. The tree diagrams are a way to keep ourselves organized. So Aiden, hopefully you're writing all this down so you have all that. The first thing we're going to go to is a table. We're going to make a table to talk about our possible outcomes. And we actually did this yesterday. We're going to do it again today because A, it's important, B, it's on your test, and I want to make sure that you're going to be able to do this on your test because now you've done it twice, yesterday and today. So for example 1, Patricia rolls 2 standard number cubes. Look, sometimes they say number cubes because they don't want to say dice because people gamble with dice and they're trying to be all correct. But you know what? Guess what a number cube is? It's a dice. Let's go with it. All right. Use the table given to find the sample space. In other words, what are our possible outcomes? So that then we can find the probability of whatever we're looking for. And in this case, it is the sum of the numbers that she rolls as a 9. She's saying, what are the probability that if I roll 2 dice, I'm going to get the sum of a 9. So the first thing we're going to do is list all the things that we could possibly get. So this right here represents all the ways one dice could land. These numbers represent all the ways another dice could land. And then we just make a chart or make a table that lists our possible outcomes. And you can do it yourself. We're going to put a plus sign right here because this word right here says sum. 1 plus 1 is 2, and then you can just fill the rest of this out. You don't even need to think about it because it makes a pattern. So you fill yours out. Okay, so this right here is a list of all the possible outcomes I could have when I roll 2 dice and I'm trying to find a sum. How many possible outcomes do I have? 36. There are 36 different outcomes that I could have, different outcomes. This right here, y'all, this list of numbers, that's my sample space. So all that, I forgot what the question is, what's the probability that the sum of the numbers she rolls is a 9? So I go back over here and go, oh, well looky here. How many different ways can I get a 9? 4 out of how many? Now I know what that bottom number is. And so that reduces to 1/9. Boom. Now that I know what my sample space or how many are in my sample space, it is easy for me to get the bottom number. So we can make a table. Another thing we can do is we can make a list. depending on the type of probability that we're looking for. So in this example, it says, at the ice cream shop, customers can choose one type of cone, waffle or sugar. One flavor of ice cream, chocolate, vanilla, or strawberry. And one type of sprinkles, rainbow or chocolate. Use a tree diagram to show the sample space, because once I do the sample space, I know what my bottom number can be in my probability. Use a tree diagram to show the sample space, and then find the probability of choosing an ice cream at random and getting a waffle cone with vanilla ice cream and rainbow sprinkles. All right. So first thing I'm going to do is forget what I'm looking for and just make myself a tree diagram. I'm going to start with the first option I have. I could get a waffle cone. Boom, we're going to go with waffle. All right, my ice cream could be chocolate, vanilla, or strawberry. And then on top of my ice cream, each I could get rainbow sprinkles or chocolate. Rainbow or chocolate. Rainbow or chocolate. And each one of the branches on the tree represents a possible outcome. Waffle, chocolate, rainbow. Waffle, chocolate, chocolate. Waffle, vanilla, rainbow. Waffle, vanilla, chocolate, and so on and so on. And so with a waffle cone, I have 1, 2, 3, 4, 5, 6 different possible outcomes. But I also have another type of cone, right? What type is that? Sugar. So guess what? I'm going to do the same thing. I could start out with a sugar cone and then do the same thing. I could get chocolate, vanilla, or strawberry, and then go back to my choice of sprinkles, which are rainbow or chocolate. Rainbow, chocolate. Rainbow, chocolate. Rainbow, chocolate. Guess how many possible outcomes I have with a sugar cone? 6. How many are in my total possible outcomes? 12. Okay, so if you've got a question that wants you to list the possible outcomes, you make a tree diagram. But I'm going to show you another way to cheat. Instead of having to list it, if all you're looking for is the bottom number, you don't have to list them all, you just have to know what the bottom number is. You can use something called the fundamental counting principle, and that just tells you to multiply the number of items in each category. So how many different types of cones do I have? How many different types of ice cream flavors? 3. How many different types of toppings? 2. Guess what? 2 times 3 is 6, times 2 is 12. That will also tell you the number of possible outcomes. So 2 types of questions could apply. You could be asked to list all your possible outcomes, in which case you need to make a tree to keep your work organized. Or if you just need to find the probability, you can use the fundamental counting principle to get you the bottom number. Now, I've done all this work. I have absolutely no recollection of what the question is, so I'm just going to go back and read it. And it says, find the probability of choosing an ice cream at random and getting a waffle cone with vanilla ice cream and rainbow sprinkles. So I'm going to go waffle cone, vanilla ice cream, and rainbow sprinkles. Do I see any more that says waffle, vanilla, rainbow? How many did I circle? This right here is just going to be one selection. That's your cone, your ice cream, and your sprinkles. So how many is there? 1. Out of how many in all? 12. So the answer to that question is 1 over 12. I have a 1 in 12 possibility of getting waffle with vanilla and rainbow. Okay, so that's one way to figure out what your sample space is. And then another way, there's a nice, neater version of it. And then another way is to make a list. But here's what I found. I can make a list, but I'm going to do it by making a tree diagram because it helps me keep my work neat. So this says Henry flips a coin 3 times, make a list to show the sample space, then find the probability of getting 3 heads. So it's not just 1. What's the probability of getting 1 head? It's 1/2, right? So we're going to figure out what the probability is of getting 3 heads in a row. So when I flip a coin, what are the two things that could happen? Heads or tails? So we're going to start with heads. Then I flip the coin again. What's the two things that could happen? Heads or tails? I could get a heads or I could get a tails. If I got a head, I'm going to flip it again. What's two things that could happen? Heads or tails? Okay. If I go back down the second time and got a tail, and I flip it for the third time, what's the two things that could happen? Heads or tails? Boom. I flipped a coin 3 times. And this says I could get heads, 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 tails, heads, tails, heads, or heads, tails, tails. Have I done all my outcomes yet? Now, what's the next thing I need to do? Start with tails. Exactly. So I'm going to start with tails. I flip a coin, I get a tail. I flip the second coin, what could happen? Heads or tails? I flip the third coin, guess what? Heads or tails? And then I just go back on this tails, tails. This last one could be a head or a tail as well. So tails, heads, heads. Tails, heads, tails. Tails, tails, heads. Tails, tails. Oops, just kidding. There. Okay, so I'm going to add these to my list. Tails, heads, heads. Tails, heads, tails. Tails, tails, heads. Tails, tails, tails. Oops. Make that a better tails. So some people, not kids, just kids, some kids or people can just make a list like this and keep it all organized in their brain. It's not my gift, so I just do it like this. Now, all that work, I don't even remember what the question was. The question says, then find the probability of getting 3 heads. How many of these have 3 heads in there? Just the one, this one right here. So it's 1 out of how many different possible outcomes? 8. The answer is 1/8. So you just need to find out what the bottom number is so that you can complete your whole ratio in your probability. Yes? Nope, it doesn't matter. So the question is, if you do it, does it matter what order? Nope. Some people will see things differently than someone else as long as you just come up with the correct number in your sample space. Now, let me show you something else. According to the fundamental counting principle. When I flip a coin, the first time, the first time I flip it, here's the second time I flip it, here's the third time I flip it. The first time I flip it, how many choices could it possibly be? The second time I flip it, how many choices could it be? The third time I flip it. What is 2 times 2? Times 2. So that will tell you how many choices you have. So if you have to list it and you're doing it like this instead of making a tree diagram, that process will tell you whether or not you've listed all of them. Okay, so I'm going to give you about 45 seconds to glue this in your notebook, and we're moving on to the next portion of our lesson on compound events. Okay, so the next thing we're going to do is we're going to talk about the difference in independent and dependent events when you are doing 2 things. So, for example, if I roll 2 dice, if I roll a dice and then I roll another dice, does what I get on the second dice depend on what happens on the first dice? No, they're 2 separate things and it doesn't even matter. However, let's just say, for example, I am getting dressed in the morning and I'm reaching in and I'm pulling out a sock and I want to pull out 2 matching socks. Does what I pull out the second time, is it affected by what I pulled out the first time? Yes, because there's 1 less sock in the drawer. So that's kind of what we're going to talk about. The first thing we're going to talk about is independent events, things that do not affect each other. So if I roll 2 dice, whatever I roll on the second dice is not affected by what I got the first time. That's called an independent event. This is what you need to write down somewhere on that foldable. This says the probability of getting A and then B, in other words, the probability of these two events happening that I'm looking for, you figure that out by taking the probability of A, or the first thing, and multiplying it by the probability of B. So right now you should be writing this down because we're about to move past that. The probability of A and B is equal to the probability of A times the probability of B. Here are some examples right here. If I roll two number cubes, also known as dice, a red one and a blue one, what is the probability that the outcome of the blue dice is a 5 and the red dice is even? So I have two dice. Whatever I roll the second time is independent of what happens the first time. The first thing I do is find the probability of the first event. The first event is getting an even number on a dice. What's the probability of getting an even number on a dice? It's 3 6, and we're going to simplify, so what is that? Now, remember that we're simplifying on this because that's going to come into play later. So we're going to put 1/2 right here. What's the probability that I roll a 5 on a dice? 1/6. So the probability of me rolling an even number on one dice and a 5 on the other is 1/2 times 1/6. 1/2 times 1/6 is 1/12. So I have a 1 in 12 chance of rolling an even on this dice and a 5 on the other. You just multiply the two events together. So let's go through this. This is a card is drawn from a deck of 10 cards, numbered 1 through 10. So basically you have just 10 cards, and each card has a number on it, and then a dice. Find each probability. So this means the probability of getting a 10 out of the deck of cards and getting a 3 on the dice. So what is the probability that I'm going to draw a 10 out of a deck of 10 cards? 1/10. So it's going to be 1/10. What's the probability that I'm going to roll a 3 on a dice? 1/6. Guess what the probability of me doing both of those things is? 1/60. I have a 1 in 60 chance of making that happen. The odds are not good. We call that very unlikely. Two prime numbers. Let's just refresh prime numbers. Let's talk about prime numbers. Let's go by, let's say the first prime numbers, 1 through 10, or 0 through 10, or 1 through 10. Okay, what are the prime numbers?
2, 3, 5, 7.
And that's it. Very good. Very good. That's it. 1 is not a prime number, and a lot of people say 9 sometimes just because it seems like it would be prime. It just kind of looks prime, but it's not prime because 3 times 3 is 9. All right. So these are our prime numbers. So in the deck of cards, remember I have a deck of 10. How many prime numbers are in there? 4. So the probability of me getting a prime numbers out of the deck of cards is 4/10. So we can simplify that. We'll just turn it into 2/5. Now, out of that, those are the prime numbers. How many of those prime numbers are on a dice? 3. Out of how many? So we know it's 1/2. And I'm going to cross out the 2 2s. And I'm going to move this over. And so what is the probability of me getting 2 prime numbers? 1/5. That's not that bad. That's a 20% chance. That still falls in around the unlikely category. All right. The next one is going to be two numbers less than 3. So out of the deck of cards, how many numbers do I have less than 3? 2 out of 10, which is what? 1/5. And then how many numbers less than 3 on a dice? But out of how many? And that's also what simplified? 1/3. So that would be, multiplied together, 1/15. It's still unlikely. And then how about 9 and an odd number? What's the probability I get a 9 out of the deck of cards? 1/10. What's the probability I get an odd number on a dice? 1/2. Going back to the deck of cards, what's the probability that I get a number greater than 5 out of the deck of cards? How many are there? 1/2. So 6, 7, 8, 9, 10. 5 out of 10 is 1/2. On the dice, what's the probability I get a number greater than 5? 1/6. There's only one. And so this answer would be 1/12. And then finally, a 6 out of the deck of cards and a 6 out of the dice. Yes, 1/10 times 1/6 is equal to 160. So when I'm trying to find the probability of compound events, or two events that are independent of each other, I just take the probability of the first one and multiply it by the probability of the second one. Now we're going to talk about dependent events. You guys are dependents. Your parents are probably looking at filing their tax return now, and you guys are considered dependents. And the more dependents they have, the more you get to write off on your tax return, because you guys are expensive. You depend on your parents. And so that's kind of the same premise as dependent events. The second one is dependent on the first one. So write this down at the top anywhere that you have room for it. This time, the probability of getting an A and a B, the probability of both events happening, is still, whoa, I'm on the wrong page. Boom, there we go. The probability of the two events happening is still the probability of the first one happening multiplied by the probability of B after A has happened. When A happens, things change, and so it's the probability of B after A. I'm going to show you exactly what that looks like. The second one is dependent on the first one. All right, so in this example, there are 6 black socks and 4 white socks in a drawer. If one sock is chosen without looking, and then a second one is taken out, what is the probability that both will be black? When you took the first one out, you didn't put it back. So the probability, this is A right here, of the first sock being black. How many black socks are there?
6.
How many in all? 6 out of 10. This time we're not going to simplify on purpose because those numbers are going to change. Now, let's say I got the black sock. How many black socks are now left? 5. How many socks are now left? 9. So both my numerator and my denominator change. That will vary. So now this is what this means by B after A. B, when A happens, how does B change? There's one less black sock, and there's also one less sock total. So then you take your 6/10 and you multiply it by your 5/9, and you can cross divide and simplify. 5 into 5 goes once, 5 into 10 twice, 3 into 6 goes 2 times, 3 into 3 goes 3 times. And then I'm just going to multiply straight across, or you could simplify that to what? 1. But 2 times 1 is 2, 6, or the probability of choosing 2 black socks is 1/3, which isn't that bad. It's a little bit more than unlikely, because there's only 2 colored socks in there anyways. Okay, so I learned in 5th period, I'm going to work through these with y'all. I let them go a little bit too soon, and there was some struggling, so I'm going to go and we're just going to work this together, and then I think you'll understand it better. All right, there are 4 green, 6 red, and 5 yellow marbles in a bag. Once a marble is selected, it is not replaced. The most important thing you can do is make sure you get the bottom number right in a problem like this. So how many marbles do you have in all? 15. And of course I spelled marble wrong, so let's fix that because that's annoying. All right, there's 15. And you know what? Just because I know every answer depends on the fact that I counted this right, I'm going to count again. 5 plus 6 is 11, plus 4 is 15. Yes, I know for a fact it's right. Okay, what's the probability that I get a yellow and then a red if I don't put the yellow back? How many yellows do I have? 5 out of how many? Then a red. How many reds do I have? 6. But I took a yellow out, so what's my total now? 14. That's why we don't simplify this time, just so that we can keep our numbers straight. And then you can simplify if you want to. 5 over 15 is 1/3, and then 6 over 14 is 3/7. And then you can even simplify that. What is the answer to this? 1/7. Now, on this particular example, the only number that changed was the total in the bag. But look what happens with this. What is the probability that I select 2 greens? How many greens do I have? 4. Out of how many? 15, because on each one of these example questions, we're starting over. Now, I'm going to go, I have a green, so how many greens do I have left? I just took 1. So how many do I have? 3. And then what's my total? 14. So in this particular instance, both my numerator and my denominator changed. Unless you're overzealous and you just reach in there and grab all of them and just go, I'm done with this math homework. All right, so that means 2 times 1 is what? 2. 5 times 7 is? Okay, now we're starting over. Let's do a red. What's the probability of getting a red then a green? How many reds do you have?
6.
Out of how many? Okay. And now I'm going back to green. How many greens are there? How many total? And so 3 into 6 goes 2, 3 into 15 goes 5, and then that's going to be 2/7. That's going to be what? 4 over, okay. And then last but not least, 2 yellows. There's 5 out of 15 yellows, correct? But if I get a yellow, how many do I have left? 4 out of how many? Yes. So we're going to, again, simplify that to 1/3 times 2/7 and get 2 out of 21. Okay. Oh my gosh, we did so much better. So just to wrap it up, compound events. The probability of one times the probability of the other. They can be dependent or independent. Independent events, you just multiply the 2 probabilities. Dependent event, you have to consider how your probability of your second one changes after the first one. How do we